Thanks for joining this tutorial session. My name is Yeung from Telstra Australia. First of all, please let me know if I speak too quickly, okay? Put your hand up and say slow down or something like that, because I will speak very quick. Okay, a little bit about myself and Telstra first. I'm a senior technology specialist in the wireless mobiles area in Telstra Australia. So I've been the technical lead for the wireless architecture and IP environment to support our packet core environment for mobiles. Basically I've been doing that for about 10 years now. And Telstra is Australia's leading telecommunications company. We have, out of a population of 23 million people in Australia, we have 16.4 million mobile services. 7.4 million fixed voice services and 3 million retail fixed data services. So we're a very big organisation that takes care of mobile, fixed, enterprise, government, etc. So we're doing anything and everything. Today I'm talking about IPv6 Single Stack Now or later. So it's more of a challenge to you during the tutorial to think about what do you want to achieve out of your IPv6 deployment. The focus is very mobiles centric, so we are talking a lot about mobiles, but some of these issues can transfer to enterprise networks as well, but it will be very focused on mobiles. So the agenda today, after the introduction, very, very briefly, why IPv6 for mobile networks. I think we've covered this topic many, many times, but I'll do 1 or 2 slides only. Just introduce to people who might be new to this what the existing IPv4 mobile network looks like. And then we'll talk about transition methods, dual stack versus single stack. We'll talk about what works and what doesn't work with dual stack, same for single stack. And then we'll look at some alternatives that you can possibly consider for your own network. And we'll have some time for Q&A at the end. So, why do we want IPv6 in mobile environments? Now, every carrier is different. You may or may not need to deploy IPv6 today, but when the time comes that you do need to do it, these might be some of the issues that has brought up the reason why. First one's obvious, depletion of depleted IPv4 allocations from APRICOT. You need to be able to sustain growth in your mobile data traffic volumes. Obviously with IPv4 public address runout, you can't really do that. Growth in the number of devices per person, so every one of you has not just a laptop, but also probably a smartphone, and probably a tablet as well, and probably a smartwatch. New devices are very session hungry, consuming multiple IPs and ports. True for IPv4 today, and it's going to be true for IPv6 as well. In the future, projected uptake of sensor networks, possibly using 6LoWPAN, or machine-to-machine communications, as well as the Internet of Things, which all uses IPv6 only. So you need to make sure that your network supports IPv6 in order to support these types of networks that are coming in the future. So public IPv4 address depletion, most operators, if not then very soon, will have deployed NAT44 in some way, shape or form very early on or very, very close to starting, either on the internet gateways or on dedicated devices, most likely on the internet gateways. So you'll be allocating private IPv4 addresses to your handsets and doing a NAT44 translation or PAT44 to your for your devices on its way out to the internet. Also, another issue that you may or may not be aware of, depending on the design of your own network, obviously, is a private IPv4 address depletion. So this could be due to perhaps you're not regionalizing your network or historical reasons in the allocation in your own carrier environment. But these private address depletion affects your APN IP pools. You can try and reuse it, but if you've got a national deployment, it may cause long-term issues. So you can't really use NAT4.4. You can offload everything to NAT4.4 architecture and avoid complications, and go to a NAT4.4 deployment. But it's really not really going to help, because it's really just a band-aid solution to a problem that already exists. Do you want to invest money to develop NAT4.4 further, or do you really want to future-proof your network solution? And the last one there is voice over LTE IMS, which really should be deployed with IPv6 only. So these are some of the reasons why you want to do IPv6 in your mobile environment. Most importantly, everything that you do, realistically, the IPv6 service should be completely invisible to the end user. With all that being said, let's have a quick review of existing IPv4 mobile network architectures. Now, this may not reflect your own network. It's a very high-level diagram, a description of what currently occurs today. Before I go into that diagram, just some terminology refresher for those sitting in here. You may or may not be aware of some 3G or 4G terminology. The SGSN MME is a signaling node for wireless environments. Just provides information to the handset about what needs to be configured. The GGSN then corresponds and responds with the requirements and allocates IP addresses, DNS addresses, etc. Via a PDP context. We'll talk about that later. The IBR in this context is called an Internet Border Router, or your gateway. UE is a user equipment, so that's your smartphone. The HLR is a subscription database, essentially storing all your MSISDN information, your customer's phone number, what they're subscribed to, etc. So it's just a big database for your subscribers. An APN is basically, it's called an access point name. It's basically functions very similar to an SSID or a VLAN. Okay, so you can think of an APN as just a group of users predetermined with this particular set of rules and subscription availability. And they have certain parameters that they will use. PDP. PDP stands for Packet Data Protocol. So it's got IP, mobile number, and tunneling information that gets sent back and forward between the UE, SGSN, GGSN. And that's where basically your IP information comes from. Now, as part of this talk, there's also one more term that's very important, which is down the bottom, called the prefix 64, the well-known number. The well-known number is defined in RFC 6416, and the end portion of the prefix is usually a slash. It's usually a 96. So IPv6 address, 128 bits, your prefix 64 having a slash 96, the remainder is a slash 32, so it's basically to support an IPv4 translated address. Okay, so just keep that in mind, that one's very important later on during the presentation. Okay, just a comparison between two. So in your typical Ethernet network, your host, switch, router, internet router. In a 3G environment, it's very, very similar. Doing something slightly different, but you can think of it like this: the UE, SGSN, GGSN, and the internet gateway. All right, these are some of the things that you probably need to do to enable IPv6 in your wireless environment. So everything that's circled essentially needs IPv6 support in some shape or form. Your UE as a start. So on the left, the UEs can be dual stack or native IPv6. We'll go through the details of that later on. Your backhaul, your radio environment, that can be IPv6. It's optional. You can keep it IPv4 if you want. The SGSN is your signaling. That just needs to be IPv6 aware. It doesn't necessarily need IPv6 on its interface. The HLR, the database, full IPv6 support. So that just means that you probably want the interfaces on. You don't have to, but the database, the software needs to understand what IPv6 is. Radius, if you use Radius, obviously needs full IPv6 support, so preferably actually with the interfaces, not drawn in this diagram. DNS, full IPv6 support with that as well, including the interfaces. GGSN is full IPv6 support, GGSN being the primary gateway between your radio and IP environment. That needs to have IPv6 interfaces for it. If you have an MPLS core, which most carriers do, then you need to turn on 6P and 6VPE. And if you are doing NAT translations or about to, then obviously you need a NAT 4.4 translator and a NAT 6.4 translator as well. And you need a NAT 6.4 because not all websites are IPv6 supported yet. So you do need to translate your users to IPv4 destinations. So this will seem familiar. So this is just the one type of high-level architecture of a current IPv4 carrier, wireless carrier network. So we just have, let's say we have two different regions. You got your UE going through the radio network to your gateway, your GGSN or EPG for 4G. Across your carrier network, which is IPv4, can be MPLS and usually it's BGP. And that goes to your internet border router, which does NAT 4.4 or PAT 4.4 translation, depending on how many you need to translate. And that just goes out to IPv4 internet. Down the bottom, they're just explaining that we're using private IPv4 addresses in this example. We're using that space to assign those private addresses to the UEs. And the CGN performs NAT 4.4 and PAT 4.4, as we just discussed. Now, you can do NAT 4.4 as well. That's two translations. But don't forget that if you do NAT 4.4, you need to think about ALGs, application layer gateways, because you have them today for NAT 4.4 translations. That means you need to invest money with your vendors or whatever your private provider is of your NAT equipment to develop these ALGs for you. And that needs a lot of development time and also probably time to test as well. If you do it, investigations and troubleshooting becomes extremely difficult. So maybe you have government regulations that require you to do investigations. That could cause problems if you're doing a double translation, which is the third point there. The fourth one is scalability and reliability becomes major issues because you need to do a double translation. So you've got to make sure that everything is planned out and managed well before you do this type of deployment. So my question to you would be, why spend on preventing the inevitable? You're going to run out of IPv4 addresses anyway. Spend wisely on long-term solutions. We'll have a quick look at transition methods. So really, there's a lot, but I'm going to focus on two. And it's very simple, just dual stack and single stack. Some more terminology refreshers. Most of you might know these to death, but I'll go through it anyway. NAT 6.4, RFC 6146, stateful translation of V6 addresses to V4 addresses in order to contact IPv4 destination servers. In order to do that, you need a well-known prefix, and that means you need to do a DNS 6.4 translation. So the DNS 6.4 is used to synthesize a quad A record from A records that return back from the server. It's usually used in the translator for communication only between the V6 client to the V4 client. And 464xlat has been one that's been heavily promoted very recently, RFC 6877. And it provides limited IPv4 connectivity across an IPv6 network. I'll describe how it works roughly later on. It's a stateless protocol translation at the very edge, so it's actually on the handset, and you don't need any encapsulation whatsoever. So it's actually a very, very good method. So there are 2 links in a slide pack. You can download the slide pack on the APRICOT website and access these links. There's 2 very good presentations about it, and also the actual RFC. So, dual stack. So what we're doing here is your radio network is IPv4 only. You have a UE that is single bearer, so one radio bearer, that has IPv4 and IPv6. So in this example, however, IPv4 has a private address and IPv6 has a just normal public GUA public address. And that hits your gateway between your radio and your IP environment. And then that's your carrier environment, which is IPv4 and IPv6 enabled. Dual stack, your internet border router or your gateway will then do a translation if it needs to go to IPv4 public internet. So you do your normal NAT44 translation for IPv4 traffic. And for native IPv6 traffic, just goes out straight out to IPv6 public internet. No translation required. Okay? You're allocating a public IPv6 address for your handset, so you don't need to do any translations. And there's no NAT66 at all. So in this setup for dual stack, it's very simple for any carrier to deploy IPv6. You have no NAT64, DNS64, or 464XLAT required. It's very simple. You have to run a single PDP context or bearer, radio bearer, for dual stack. That requirement is basically there to reduce licensing costs because it costs a lot of money for radio bearers. If you want to do dual stack, it's best you have a single bearer. IP network core is enabled with dual stack, the purple one in the middle. So with this kind of setup, you can introduce it very quickly to your customers with minimal risk. And most existing applications work perfectly fine with this kind of setup. The second transition method is enabling single stack. So I'll describe what's going on here. So instead of enabling dual stack on your handset, you enable a single bearer IPv6 only user plane. So basically what that means is the gateway is allocating an IPv6 only address to this handset. There is no dual stack, there is no IPv4 allocated to the handset. It doesn't talk IPv4 to the network. Your radio network is still IPv4, that's fine, it's just transport, no issues there. When it hits the gateway, it uses IPv6, so that's why these interfaces on the gateway need to be IPv6 enabled. Okay, they need to have IPv6 to talk IPv6 to the rest of the network. The core is still dual stack, okay, because you still need to support your legacy users on IPv4. And when you get to the gateway, your IPv4 traffic goes through the gateway and does the NAT64 translation. So this one's slightly different. It's a public v6 to a public v4 translation to IPv4 internet. And then a native IPv6 just goes straight through to native IPv6, no translation needed. So your stateful NAT64 replaces your NAT44 for IPv4 distant traffic. In this setup, a DNS64 absolutely has to be in the path. Okay, it's needed because your single stack IPv6 needs a way to understand how to get to IPv4 destinations. Now, 464XLAT by itself doesn't activate unless there is an IPv4 literal or a non-protocol agnostic application being used on the device. So we were talking about 464XLAT on the device. It doesn't actually get used. 464XLAT doesn't get used unless it's something that the device doesn't understand IPv6 with, doesn't even get called up. So you need a DNS64 essentially to get to IPv4 public destinations. But having said that, the UE needs 464XLAT or something similar due to the fact that there's a lot of IPv4 only applications still out there, and you just need it. Right. Okay, so why do we need it? We're projecting about 50% of your traffic, could be more, could be less, on a single stack IPv6 handset, to get to about 50% of the traffic that's existing in your network. So that's traffic like Facebook, Akamai, Google, etc. Okay, they will go straight to the IPv6 internet because those websites are all IPv6 enabled today. 49% of it is going to go to IPv4 only, so you need a translator. Okay. So this is like just your small businesses that connects to a web host, and the web host may not have IPv6 enabled and only has IPv4. And then there's 1%. These are the applications that have IPv4 hard-coded into the application. The literals. Or they don't understand IPv6 because they're programmed specifically for IPv4 only. And with 464xlat, you can do that stateless translation from IPv4 to IPv6. And unless we solve this 1%, really you can't get rid of 464xlat. I'm hopeful that we can get rid of it within 10 or 20 years, but it's going to be hard. But until that time, we need some sort of stateless translation on the UE. Dual stack. Some good things about dual stack we talked about just before. 100% IPv4 and IPv6 content access. So you don't need to worry about your content access, it just works. Ease of migration. It's going to be cheaper for your organization to get your users onto IPv6. It's there, so you don't need to do any new hardware, don't need to do any translations whatsoever. Your users can get to native IPv6 websites straight away, your Facebook and your CDNs like Akamai. Provides production IPv6 experience to your customers, and while you have the reliability and steadiness of existing IPv4 implementations. So if there's anything wrong with your IPv6 setup, well, your users are going to be fine. They can continue to use IPv4 with no issues whatsoever. But biggest problem with dual stack, it doesn't solve your IPv4 depletion problem. If you have a private address depletion issue in your network, then this doesn't solve anything. You're still using IPv4 addresses, whether it's public or private addresses. The other thing is, if you think longer term, so you've deployed dual stack, and you haven't deployed any translation mechanisms. So what is your end strategy to get to IPv6 only? If there's no strategy to go to single stack, it will end up costing your organization more in the long term. And that's because if you don't have that strategy in place, it's going to mean that you need to do more planning work to convert your network from dual stack into single stack. You can't just turn off IPv4, by the way, it doesn't work like that. It gets worse. Authentication and other services may be inadvertently impacted. Remember, you have two IP addresses on your devices. So your users have two addresses to identify them, not one. Because of that, troubleshooting for your users are also going to become harder. You've got to deal with two different protocols now, and one of them is going to be translated as well, IPv4. So, okay, the third item is how do you introduce a single stack service into a dual stack service in the future without affecting your existing users? Okay, you may inadvertently translate them. So if you have a dual stack only service today and you deploy single stack service, and we were discussing about NAT 6.4 and DNS 6.4 before, and you introduce a translation service onto your network, your dual stack users on IPv6 could inadvertently be translated. Now, the fourth item here, there's some challenges with this one. DHCP prefix delegation, or DHCP v6, isn't on any devices today. So how do we allocate a viable and usable IPv6 GOA to your tethered device? This is like your tablet connecting to your handset, connecting to the internet. Well, we don't have NAT6.6 today. So how do we do this? If the UEs are configured with dual stack in a single APN and you sell it to them and it's locked, how do you change them to single stack in the future without user intervention? So you don't want the user to do anything. How do you change it? Yes, granted, you can do that on the HLR. You can do that in the database when they are attached to the network as well. But do you want to change your entire customer database to fit this? So, and there are significant changes to your packet core environment as well. And you really don't want to affect all your customers that are on the one APN that you deal with. Biggest problem I see so far, though, has to be international roaming. There are some networks out there that are still running 3GPP release 8 and below networks. Those particular networks, the biggest issue is the SGSN, the signaling node I was talking about. That signaling node doesn't understand dual stack. So what happens if your user, which is configured as dual stack, goes into roaming into one of these networks? They get blackholed straight away. So let's have a quick look at IPv6 single stack. There are pros and cons with single stack as well. If you use IPv6 single stack, you don't use any IPv4 private addresses. And you translate to IPv4 public only when required. Simple, that's the rules of NAT6.4. Your native IPv6 traffic doesn't need translation, just goes straight to the major sites like Facebook. Okay, no translation needed, very, very good. And you simplify your traffic flow, so it's very easy to understand how the traffic flow works if you don't need to deal with two different protocols. But there are problems with single stack as well. Every device needs to support 464xLAT. There are still some issues with literals and domain names not being resolved by DNS 6.4. You have to have that stateless translation on the device itself. It's a more complex migration strategy because you have to set up single stack. So there's no guarantees that everything's going to work day one. I can tell you now DNSSEC is not going to work. More complex network architecture when NAT6.4 is installed. And not all NAT6.4 ALGs are going to be supported. So we can see so far that there are advantages and disadvantages between both solutions. Either one by itself is not going to meet your customers' demands and business needs into the long-term future. You need a solution that is better than either one of them. So what do you do? I'm going to give you some suggestions. Some of these are good, some of these are bad. We'll have a look at all these alternatives and you can have a think about these. We talked about APNs before. They're like VLANs or SSIDs. So the first idea is you can create multiple real APNs that support IPv4, IPv6 and dual stack and separate them all. Very nice. You have to run separate APNs for each protocol type. So you've got a v6 APN, a dual stack, and a v4, and they all hit your core. Your v6 needs to do a DNS 6.4 translation. Your dual stack probably doesn't need a translator, so you need a separate DNS. Okay, and your v4 is just your normal DNS, so it doesn't need to do a DNS 6.4 translation, obviously. And you do your NAT4.4 or NAT6.4 on here. And goes out to the internet, which is very clean because that means your dual stack users don't get inadvertently translated. And you may have finer control of your network. Multiple APNs, however, will cause havoc on your device provisioning team. Suddenly your device team they really aren't going to like you, because they would prefer a device that is configured, or every device to be configured almost identically. And having multiple different configuration types on the devices is just going to cause trouble. So really you want to prefer a common APN, just one APN, and a common setting across all your UEs as well. Now, with this configuration, BYOD is going to be a big problem as well. Bring your own device. The users will have a default setting, but they can easily modify the APN settings as well. And if they misconfigure the APN in some way, shape or form that's not standard, it will cause issues to that particular customer. So what if you have a DNS dual stack only APN and your user inserts a single stack only device onto your dual stack only APN unknowingly? What would happen? So your single stack user isn't going to get a NAT64 translation. They're not going to get to IPv4 destinations. What if you have a single stack APN with v6 only, and your user changes the PDP to dual stack and expects IPv4? Well, they're not guaranteed to get IPv4. It depends on the application, and they might get translated as well. Applications that don't understand IPv6 is going to fail with single stack v6. We're talking about 3 different APNs, okay? So if they don't understand IPv6 and you put them onto a single stack IPv6 APN, it's not going to work. In some instances, 464X will fix it, but if not, then the user needs to fall back to v4 or dual stack. Now, there's a possibility that they may select dual stack and not IPv4 only, and that means they still get an IPv6 address, and they may have intermittent problems getting to their destination. The devices are usually pre-configured with appropriate APN settings. It depends on each carrier. Some are different, but they're usually pre-configured. If not all APN settings are present, then the user has no way to default back to IPv4 either. All right, so not really the best solution. The second one I have here is, let's just create a single APN that supports both dual stack and single stack. That's what we wanted, right? Right, but you need to, so what you need to do here is you need to create a PDP as dual stack. So set your gateway to allocate both IPv4 and IPv6 in the same APN. That's what you got to do. You've got to set up as dual stack. Unless you have another method to simultaneously allow v4 and v6 single stack UEs on the same APN. Now, using this method, you have no control over what protocol your user is actually doing to access your network. You have to support all 3 options. So your user has the option of selecting v4 only, v6 only, and dual stack. In this setting, your GGSN can support all 3. But you have no control over what your user is doing. But here's the problem. As I discussed before, you have a DNS 644 single stack. So your dual stack users may experience some inefficiencies while using your network because the DNS 644 is inadvertently doing some translations. You have no way to stop this because you don't know when it's going to happen. And because of that, users who are on single stack who switch to dual stack doesn't have any resolution to this until they switch back to IPv4 only. So close, almost got it right. We'll try this other method then. Let's try creating, so we've all heard of what VLANs are. We all know what switched virtual LANs are. Okay, you could create a virtual, a logical VLAN. So it's the same kind of methodology on APNs. You can create a logical APN. So let's create logical APNs that support both dual stack and single stack on to separate a real APN. So basically, it's just two different logical APNs with different configurations that point back to a real APN. If we do this, there's a huge advantage. All right, on the handset, it looks the same, but logically, they're configured slightly differently. You can separate your real APNs, meaning that you can use separate DNS server names. So the DNS 6.4 problem doesn't exist anymore. The same problems as it's the same problems as the single APN, but what control mechanism do you have to determine which real APN the user goes to? There's not really many options to help you push your users to a particular APN unless you use the username field in your APN configuration. Now, there's a couple of problems with this. The username field isn't really useful for this purpose. It's not to help you redirect to different APN names. So it's bad to use a field that isn't designed for that method. What if you need to use the username field for logins? You can't do this. You have a whole deployment of handsets with the username set for a purpose that the field wasn't deployed for. So you're going to deploy a lot of handsets with this configuration. You're not going to let the user modify it. So if you need to change something or add something in the future, well, you've got all these handsets with this pre-configured already. The biggest problem is your BYOD users. Well, they won't know that you've got a username setting. So you've got to let them know what that setting is. So if they set it up and they don't know what it is, they've incorrectly configured it and it's not going to work. So there's nothing we can do anymore. Maybe this is the best option. Let's create a real single APN that supports dual stack and single stack and use false IPv6 DNS resolver addresses. So this is a method to try and fake the UE to the correct DNS. So you don't do that translation. The DNS configuration is slightly complex. So the DNS has an IPv4 and IPv6 interface address. Your inbound filter on the DNS will point to a particular logical partition in the DNS based on these filter rules down below. So the first one is your IPv4 logical partition just does normal IPv4. Except you do a match destination that's its own IPv4 address. So you use the IPv4 address of itself. Your v6 partition is then enabled with with DNS 6.4. And then you add a match destination to the IPv6 interface of the DNS. Now, GGSN is where the configuration gets more interesting. Your v6 DNS name is the same as before. Your v4 DNS name is the same as before. And for your v6 primary DNS, you put a false v6 address to point it to the IPv4 address. Okay, so that's what you put in. Colon, FFF. Let's say that's your DNS address for IPv4. And then in your secondary DNS name server, you put in the real IPv6 address of your DNS resolver. So what will happen in this configuration is when your user receives either both the v4 name servers or 4 name servers for dual stack, or both IPv6 name servers for IPv6 single stack. So your v4 users will get the v4 only name servers. Okay, it's the same as before, so there's no difference. So the difference is all done on the IPv6 name servers. Your dual stack users are going to get all 4 of them, and then your IPv6 single stack users will get these 2. Okay. What's going to happen is your dual stack UEs are going to accept the primary IPv6 DNS name server because this false address is resolvable with IPv4. Okay, and that means the secondary field can be used for your backup name server. What gets really interesting is the single stack. The single stack will try and attempt but fail to reach the primary IPv6 name server. So it can't understand this. okay? And then retry with the secondary. So what you've done there is your dual stack users will never hit DNS 6.4. It will never hit, you'll never get the issue of the inadvertent translation with DNS 6.4 for dual stack. Must be the best option we've got. Until it's not. It's not. What happens if your IPv6 primary name server fails? All right, if that fails, well, your dual stack users are going to hit the secondary and you get your translation problem again. What if your secondary DNS fails? Well, there's no third or fourth, you can't really configure that. So if that happens, your single stack users won't get the NAT 6.4 or DNS 6.4 translation either. So back to square one. All right. So there are 4 carriers in the world who have deployed IPv6 today. All right, probably more than that now. I can't tell any names, but first one's done it with dual stack. Second and third one's done it with single stack, NAT 6.4, DNS 6.4, and CLAT. And the fourth one has done it with single stack, dual stack for the UEs. So they're supporting both. They've done it with a NAT 6.4, with DNS HD and CLAT. And every carrier will have a unique set of circumstances to dictate which translation method that they use. Okay, there's no standard way of doing this. So all I've done today is to show you all the different issues you have if you have to do this. Ultimately, you have to decide which method is best for your network. But important thing is you have to have a long-term strategy to the eventual deployment of native single stack IPv6. NAT 6.4 DNS HD. What is DNS HD? It's heuristic discovery. So, what I hope today is you take this one away, if anything. Create a single real APN that supports both DSN SS and use RFC 7050. So, the DNS configuration. It's all in the DNS this time. Your IPv6 logical petition processes quad A requests normally. Okay, so you create an IPv6 logical petition in your DNS. You don't need a DNS 6.4, and you add a match destination to its own IPv6 interface. You bind the well-known names ipv4.google.com and ipv4only.arpa and point them to your ANS. In your ANS, manually map the IPv4 translated address into a quad A entry to any well-known prefix that you've got. So you determine what the prefix is. Okay, you can manually map the IPv4 address into a quad A entry for these 2 domains. Now, why am I using these 2? It's because RFC 7050 is actually implemented in RFC 6877. It's on 464 XLAT. So when you turn the device on, it automatically looks up these two well-known names. So what you're doing is pointing the DNS back to itself to look at the IP address for these 2 domains. Because your ANS has the well-known prefix determined, it's going to respond with the well-known prefix back to your handset. Why do we need that? Because we then need to push it out to DNS, so to NAT 6.4 translation. So the UE is going to receive the well-known prefix for both local synthesis and for detecting synthesis done by the DNS 6.4 server on the network. What about our GGSN? So our GGSN is configured with an IPv4 and an IPv6 DNS name servers using real IPs. So there's no false IPv6 addresses or anything. Don't need to fake it into doing anything. If you have this configuration, then your UEs will get both v4 name servers for single stack v4, or 4 name servers for dual stack, and both IPv6 name servers for v6 single stack. Brilliant, right? And your DNS redundancy is maintained as well. Does mean that your UE needs to support 7050 and 6877, but it should already be in Android 4.4.4 as part of 464 XLAN. So, the final configuration I would like to promote to all carriers who are in this session is SSDS UEs using NAT64 with DNS HD and 464 XLAN. Is it really the best solution? It probably is, but in a wireless carrier environment, your APN config is all done in the GGSN. So the primary goal of RSC 7050 is to let the UEs do local IPv6 synthesis and avoid NAT64 in a dual stack deployment. So, think about it, it's an extension to DNS 6.4. Given we're looking at a single APN deployment to support all these different methodologies, there's actually a relatively simple fix on the GGSN that you can do. So your UE can be configured to send IPv4 only, dual stack, or IPv6 only. Needs to reach the GGSN anyway, because the GGSN needs to send an IP address back to the handset. So if the UE sends a PDP request to the GGSN should respond with the required DNS name servers. So if it's v6 only, it just sends the v6 name servers only. If it's IP, and those IPv6 name servers only has DNS 6.4 on it, obviously. If it's dual stack, then send the name server of the of the DNS server that doesn't have DNS 6.4 enabled. Simple as that. So you can actually fix the problem on the GGSN, because modifications to the UE takes months and a lot of effort, because you've got to deal with multiple device vendors to fix these problems. But it's the same issue on packet core equipment. So your GGSN also takes months for your manufacturers to come up with a solution. You've got to go through testing, install, etc. The question you've got to ask yourself is, which element stays in a network more permanently and requires less interaction with multiple vendors? In the end, though, it's all about the customer. So we know IPv6 doesn't work with everything, but you've got to make it the least painful for the customer if they need to fall back to dual stack or IPv4 only. I can't stress that enough. You've got to let them fall back. Make the solution work for long-term goals of the business. Path to native v6 and removing the need for private v4 addressing. That should be the goal. You still need public IPv4 addresses. You can't escape that. But as I mentioned, we are expecting about 50% of our traffic to be native v6 the moment you turn this on. So public v4 usage is going to slowly reduce over time. It's not going to happen straight away, but it will reduce. Ensure your vendors understand the importance of supporting these RFCs. Okay? They're all on the device, and v6 in general for their software and application development. It's crucial for the transition phase to go to v6 native. They need to start supporting it now. The fourth one is ensuring the customers are well informed and have avenues to find answers easily during the transition. Because the worst situation you can possibly face during this is defaulting everyone back to v4 because something was broken or misunderstood. So, just give you a quick status update as well about what Telstra is doing about IPv6. We've been testing v6 for about 4 years, and we think we're at a stage that we're very close to doing something as a pilot. First thing is we're recommending 4.4 above Android for v6 launches. Obviously, Lollipop is already out, even better. But if you've still got legacy handsets, then anything that's 4.4 and above. It's the most stable operating system so far, by far the largest improvement to solve any MTU issues and 464xlat related issues that we've identified. Second one is we've been looking at Windows Mobile. Windows Mobile has 464xlat as well, but they've only done it for the dual stack context for some strange reason, not v6 only. So we're still pushing that, and if there's any carriers in the room that wants to have a chat, I'd love to talk to you about that as well. We can push together. NAT64 ALGs, it's becoming has some issues sorting out some 464xlat source addresses. So the two don't really work together all that well at the moment. My recommendation, because everyone uses a different vendor for their gateway, just test thoroughly with your vendors, because before you do anything and launch it to consumers, just make sure the ALGs that you need are actually there. Now, I've talked about the DNS HD before. Think carefully about the logical flow of the DNS, because there are better ways to do it. There are definitely better ways to do it, but that is what the RFC has indicated, but there are better ways. Tethering is a big issue that we found. And I recommend to you to attend the task force meeting tomorrow at 4 p.m. In room 501, and we can go through some tethering issues at that time. So just one more thing. We've talked about international roaming before. So I've taken my phone to Taiwan with a Telstra LTE SIM and set my APN protocol to IPv6. So that's this bit here. All right. You can see here that it says roaming, and you can see an IPv6 only address allocated to my handset. And to prove that it is roaming, I've got that R symbol on top of the radio there. All right. This is just proof that single stack IPv6 international roaming it does work. So there's no reason why we can't do it. The only reason why we can't do it is not all operators support IPv6 today. So it does work. We need more carriers to support v6 and 3GPP release 9 and above. We really want that. Keep in mind that dual stack isn't recognised by older SGSNs, and so some customer connections are going to fail if you choose to use dual stack. That's also important for international roaming, because you can see here there's actually two settings on the UE. One is for your local connection and one's for your roaming connection. So my recommendation to all of you here today is to set all your APN roaming configuration, well, at least for the next 2 years, until the situation improves a bit more, to IPv4 only. And there's going to have to be more negotiation between the carriers in order to have all of our users set to this. These are some of the challenges that the carrier community really needs to overcome together as we move to enabling IPv6. PCRF internet working over the S9 interface. PCRF is a subscriber information type database. If you're from a carrier wireless, you'll know what I'm talking about here, but it's about roaming and swapping the subscriber information for your packet call. And this is the big one, voice. Voice over LTE, IPv6 enabled, international roaming. That is the big target, and that is the really challenging one. So in conclusion, every carrier will have a unique set of circumstances, as I mentioned. It will dictate which transition method you will use. I'm not saying one is good, one is bad, okay, but just noted some of the issues that you may encounter. There's no standard way of doing this. You have to look at your own network. Avoid NAT 444. Any investment really should be placed into long-term solutions for IPv6 that will transition you more quickly to v6. But you can do NAT or PAT translations in the short term. That's no problems. Dual stacks required in most circumstances, but you can run certain surfaces over v6 single stack today. So I hope this presentation has given you enough information to ask yourself, why can't you do both simultaneously? And you can do single stack right now. So thank you very much. I'll take questions if there's any.
Isani, thanks a lot. The question about VoLTE, you mentioned about VoLTE international roaming over IPv6 be a very challenging one. What are the perceivable challenges you have in your mind? And what would be the potential solutions?
There's a new standard out called Voice over LTE RAVEL. Don't ask me what the acronym stands for. It's a new one. It's part of 3GPP release 11. And as part of that, there's information on how to do voice across for international roaming. You need to consider it as part of data, but the problem is data is not cheap for international roaming. And exactly how do we quantify QoS for voice over GRX or IPX? Those are some of the questions that we've got to talk about. Any other questions? If not, thank you very much. Enjoy the rest of your conference. Thank you.